All right, hi again. Today we are going to do the last section of Chapter 4. This will be the last section before our third test. So I will be getting information about the test to you shortly. We will also have a review session online. I might also do a video of the review session. I'm not sure yet. So anyway. Let's get started with today's work though. So here we have, okay, so this should look very familiar. We have a graph here, goes from A to C this time, and we know if we take the antiderivative and evaluate A and C, we'll get the area under the graph. What they're showing here is if this section of the graph, so we'll call that section 1, and this section of the graph, let's say they were defined by different curves. So I couldn't just use one curve and one antiderivative to get the whole area. What I can do is take the antiderivative, evaluate it, get the area from A to B. So get the area of this section, section number 1, and then take the antiderivative from B to C and then add those two areas together. Okay, it's nothing you haven't already done. What this is called the additive property, meaning if I have two separate sections and I want to know the total area from those two sections, I can just add them together. So there might be times where we have to take areas of sections separately and then add the sections together. Okay, but the meat of this chapter is going to be the area between two curves. Okay, so here we have this area that's in kind of a goldenrod mustard color. That is the area between the curve f of x and the curve g of x. Okay, so we want to find this area. What happens if I find the antiderivative of f of x? What area would that give me? Well, that gives me this whole area all the way down to the bottom, which is not what I want. I only want this area in gold. Okay, well, the area down here is the area under the curve g of x. So if I get the antiderivative of g of x and subtract it out of the antiderivative of f of x, so get rid of this section, what I'm left with is the area that I wanted. Okay, so we are going to take the antiderivative from a to b of f of x and then subtract the antiderivative from a to b of g of x. But we're going to subtract the two functions first, and we'll just take the antiderivative of the simplified section. Okay, so here is our first example, and this is just a little bit different than what we had before in that this time it's bounded. They did not give us A and B, but they said that the region is bounded by the graphs. That means that we want these intersection points, and we're going to have to figure out what those intersection points are. So we're going to have an extra step in that we are going to have to figure out A and B. I'm going to give you some steps for these kinds of graphs. So let's go ahead and do that. Step 1 is going to be to set the functions equal to each other and solve. Now this is so we can get A and B. Those are the spots where the functions intersect. Oops. Okay, so that's step 1. We have to set those two functions equal to each other And we have to solve so that we can get a and b. We're going to need that for the ends of our integral so we know how to evaluate this. Step 2 is to, I'm going to change my mind here, determine which function is on top. Okay, now that is very important. Let's go back up here and look at this. Now, I would recommend that the first thing you do is to put both of these in your calculator. Y equals, you can do a y1 and a y2 and you'll be able to see, and you might get a visual. Visually, we can see that f of x is on top and g of x is on the bottom. We have to have the correct one on top. We have to know which function is on top. And there will be times when we might not be able to see that with our graph. So we need another way to be able to do that. Okay, so if you can't just look at the graph and see which function is on top, then you're going to use a number in the interval. Remember, the interval is a and b. It's that area. We're going to plug in a number in the interval to determine that. And you'll see that when we do the example in just 1 minute. Step 3 is to find the antiderivative. And then step 4 will be to evaluate the antiderivative at a and b. Okay, so those are your 4 steps. You might want to take a minute and write those down. So let's go ahead and do those for this particular function. Let me see what we've got on the next page. Oh, yep. Okay, so step 1, set them equal to each other so we can find out where they intersect. Okay, so here we have f of x was 2x plus 1. We're setting that equal to x squared plus 1. So let's subtract 2x from both sides and subtract 1. Subtract 2x, subtract 1. Okay, on this side we are left with 0. Over here we have x squared minus 2x, and the plus 1 minus 1 are going to add to 0. We have a GCF of x, so we're going to factor that out. So we are left with x times x minus 2 equals 0. Set each factor equal to 0. Okay, which means x is 0 and x is 2. This is your A and your B. Okay, so now we know where they intersect. Okay, the next step is to figure out which one's on top. So, and I'm going to do this. That was step 1, finding where they intersect. Step 2 is to determine which one is on top. So we said that A was 0 and B was 2. Okay, in order, f of x is 2x plus 1, and g of x is x squared plus 1. Okay, in order to figure that out, I have to pick a number inside this interval. And sometimes the number might not be a whole number. That's okay. Decimals are numbers too. In this case, we can just pick the number 1 fits nicely inside the interval. Do not use a or b. It has to be a number in between a and b. Okay, and then we evaluate each of these functions at that number. So we chose 1. So 2 times 1 plus 1 is 3. And g of x, so g of, 1 equals 1 squared plus 1, which is 2. Okay, which number is bigger? Well, it is the 3, which means that tells us that f of x is on top. Okay, if you do not identify the correct function as being on top, the answer will not be correct. Okay, step 3 is to take the antiderivative. So here's your integrand symbol from 0 to 2. Those were the numbers we got in the first step. Okay, and we determined f of x was on top, so we have 2x plus 1 minus x squared plus 1 dx, and there's a reason I put that in parentheses. Again, remember, we are subtracting a whole function. That means the negative has to get distributed. So let's do a little simplifying here. Antiderivative from 0 to 2. Okay, so we have 2x plus 1 minus x squared minus 1. Okay, that the 1's are going to cancel out. We are left with 2x minus x squared dx. Okay, that is what we're going to take the antiderivative of. Now we need to take our antiderivative. So the antiderivative is 2x. My exponent was a 1, so we're going to add 1 to that and divide by that new exponent. X, it was a 2, it'll now be a 3 divided by 3. Okay, and this is going to go from 0 to 2. All right, and if you, well, let's simplify that a little first, sorry. So we have the 2's will divide out, so we have x squared minus x cubed over 3, and we need to evaluate that at 0 and 2. Okay, so we have 2 squared minus 2 cubed over 3 minus 0 squared minus 0 cubed over 3. Okay, so on this side we're going to have 0, and here we have 4 minus 8/3. Now, since I'm not doing this in a calculator, I'm going to go ahead and change the 4 into thirds. Remember, I'm going to multiply by 3 over 3. So I get 12/3 minus 8/3 equals 4/3. Okay, and I kind of ran into, let's pause for a minute. This was the end of step 3. When we start plugging the numbers in, I should have labeled that as step 4. So this last part was step 4, evaluating. The final answer, our area, is 4/3. Now, I would encourage you to do some of the problems from the book. In fact, I believe that the problem I chose for your next quiz comes directly out of the book for the area bounded by 2 graphs. Okay. We did all that. Okay. The last part we need to talk about is average value. Okay, and the idea here is that, let's go to the picture for 1 minute and see if this makes sense. Okay, so we have different areas, like the area here is this tall and the area here is this tall. But over the whole interval, that is the average area. Okay, so the area here is smaller, the area here is bigger. We have an average of the area. Okay, so we are going to figure out the average of the area by taking the length of the interval, so 1 over b minus a, the antiderivative from a to b of f of x dx. Okay, so we're still getting this section here is the area. That's the total area. And we are going to divide it by the length of the interval. Okay, it's like we had the different rectangles and we're dividing it by the number of rectangles. So we're getting the average area over that whole interval. All right, so let's do an example of that. Okay, so in this example, a is 0, b is 2. So we have 1 over b minus a, the antiderivative from 0 to 2 of x squared dx. So let's go ahead, I'm going to drag this along, and let's get the antiderivative. So we have x cubed over 3. We need to evaluate that at 0 and 2. Now again, I'm doing it by hand. You would probably do this in the calculator, but I'm going to, oops, don't know what happened there. I'm going to evaluate this inside part first. I want to get the total area first, and then I want to divide that number by 2. Now, in this case, it's going to be 2 fractions, so I just multiply fractions straight across. But so I plug in 2, so 2 cubed over 3 minus 0 cubed over 3. So I have 1/2. 2 cubed is 8/3, and we're subtracting 0 cubed over 3, which is 0. So I have 1/2 of 8/3, and we just multiply straight across. We get 8/6, which simplifies down to 4/3. So my average over the interval is 4/3. Okay, remember, you are looking in the problem for the words average value, and that will let you know that you need to do this 1 over b minus a in front of it so that you can get the average over that interval. All right, that takes care of our lesson for today, and I will be talking to you soon.